Ready? Perfect. So, good afternoon, everyone. This talk is on being Eeyore in Infosec. I'm actually Stefan Edwards. I go by a Twitter handle of Logical. All this usual sort of like adjectival bullshit that people give about themselves. But I basically do a large number of things. I do application security, I do some network stuff, defer, coding, etc. And I'm pretty much all over the place. So although Invisium themselves is pretty much an application security company, this talk is basically on how everything in Infosec is terrible, not just AppSec. AppSec is easy enough to pick on. We can find all sorts of things that are wrong with AppSec entirely, but I thought I would just include everyone else in this. So basically the the gist of this talk is that there's a formulaic way of approaching security. No one will ever do it. We're going to talk about a little bit of the historical things that we've done to secure items, right, infrastructure, etc., and why no one has done those. And then we're going to talk about some of the future things that we could be doing and probably won't do. And we're basically going to be focusing and using Winnie the Pooh throughout, and sometimes Winnie Pooh. So if you're familiar with the Soviet system, there's actually a clone of Winnie the Pooh. So our gentle stroll through the 100-acre woods here will be, I'll give a quick overview of what I mean when I talk about security, right? Because it's slightly different than what several other people will mean when they're discussing this. I'll talk about process failures. So these are the sorts of things that businesses do. It's not necessarily like a NIST 853 style process failure. This is more of a general issue that we have with the way that we design and implement systems. I'll talk about some cryptographic infrastructure. It'll basically compare and contrast where we were with X509 certs versus SPKI. We'll talk a little bit about operating systems, why Unix won, why that's awful for the rest of us. I was originally going to include frameworks, but as I'm at 75 slides or so already, I figured that I probably will bore you to death by the end of 50. So I cut that whole section out as well. And then I'll talk a little bit about network protocols, why they're broken, why they will basically never get better. We'll talk about programming language theory, which is something I'm extremely interested in. And then we'll talk a little bit about a thought experiment that I've been working on myself for, about 10 years. So all of my talks have themes, so you were just unfortunate enough to end up in the Winnie the Pooh themed one. I also have a talk on programming language theory that actually uses Shakespeare. But, all of my talks always have some theme, and you just happen to hit this one. So when I talk about security, I don't just mean the absence of vulnerabilities, right? I actually mean a whole process here. I'm talking about design. I'm talking about the denotation, or what the actual system means itself. I'm talking about models of security that we can actually have. I'm talking about the centralization of those controls, of security controls that we can have, right? So you want, if you're talking about input validation or you're talking about ingress filtering, you want to have those in a single location instead of spread out throughout your entire application or throughout your entire infrastructure. I'll be talking about decentralized implementation, right? So when you think about X509 certs versus SPKI, or you think about the various ways that we can implement things, there's differences in who has control, what that trust chain is, etc. And we'll talk about what I actually mean when I talk about secure. So when I'm thinking about security, I think of that formula, right? I think of all of those things together. Now, the thing that most people are not normally used to are two. Denotation, specifically denotational semantics of what your application actually means, or what your network actually means, is the first thing that most people are not aware of, right? So when you have this sort of, when you have a denotation or a set of semantics for an application, you can actually understand at any given point what is or is not valid semantics for your program. Now, where is this actually interesting for us, right? Well, you could have something like a state machine parsing bug in an OpenSSL situation, right? So you should know the state transfers for your protocol, but you don't actually know them, because there's a way to actually insert yourself into a different area in the state machine logic. You have different semantics at that point, right? It could be interesting for programming language theory purposes as well. So basically what we're looking for is something that describes the structure and the flow of a program, of a network infrastructure, a protocol as we go through. And we have some formal rules about those. The next thing is modeling. Most people have probably seen the lower part of this. This is obviously Java. But the upper part is something that most people are not aware of. And this is actually called JML. It's the Java modeling language. And basically it's designing, or it's setting up a specific set of contracts that your application actually has to validate and verify prior to not even execution, but compilation. So basically this is just saying that at any given state in the program, you have to require that the amount is greater than 0, and the balance is less than max balance, right? So when we're doing this here, we're saying that the internal side of balance is assignable, and we're setting up some other structures, some other invariants for an application. Now, this is something that I've only seen one client actually do. It's pretty rare for anyone to have this level of understanding. I wish more people would have it. The other fun one is that they've defined all these things, they did them, they have it, they have some system that actually goes through and checks their JML assertions the entire way through. It was last touched in 1999. It hasn't kept up with the rest of the application, and no one actually cares that there's all these process failures throughout the entire build. But those are the two things that I think are the most interesting. Now, why do we actually care about these sorts of things, right? Well, we care because we're actually looking at not just security, but we're looking at correctness, right? We're looking that an application is or an infrastructure is actually doing what it's supposed to be doing. So I actually have a little bit of a heresy here, right? I actually think that you could design something to be unhackable. I think it's possible, right? I think you could come up with something that if you threw tons of money at it, if you spent time, if you spent people, you spent processes, you spent the money and allowed anyone to stop the process at any given point in order to have a security issue, you could actually have something that's unhackable. Now, do you actually need to do this for the vast majority of your infrastructure, right? Has anyone actually done a full modeling of their entire infrastructure, application, anything? No one? I love how Dave, technically my boss, is laughing at me the entire time, because that's one of the services that we offer. But it's honestly outside most people's budgets, right? You don't need to have these sorts of practices because you don't actually have that sort of threat model. So this will never happen. You'll never actually have something that's unhackable. You could potentially do the unhackableness, but no one's actually going to invest that sort of time, that sort of effort into it. So I thought we'd start with process failures, because these are the easiest ones to actually get wrong. And they're usually surprising ones, right? We all think that we communicate really well. We think that we talk really well. We think that we express our ideas. If you talk to your business side, they're going to just say that, everything that they've ever given you was very clear, very common, and as a developer, you're just not going to get it, right? So the problem is that we as devs and we as Infosec are both cost sinks for a business, right? We're not actually doing something for them, right? When they think of something, they think of the product that they give out. They think of the thing that you've actually designed. They're thinking of those areas. Whereas devs and Infosec are just, money, right? That's all we do. We just cost them money. So it leads to a slight problem here, right? Where we have Infosec, who's OWL, right? Someone who can actually literally just fly somewhere. We have Rabbit, who's business. They're super excited about getting the product done, getting out of the pit. And we have Winnie the Pooh, who's like your PM, who's super happy that anything gets done. And so what we do is we actually send Piglet out, the developer, and then we're surprised when they come back with flowers when we need rope or anything else of that nature, right? So this entire process, the way that we actually go about these things, the way that we actually handle devs, we don't come up with some formal design. We don't empower them in a way that they can actually implement something useful, means that we will just continue to have flowers when we're stuck in the pit. So we expect devs, we expect DevOps, admins, whomever, to do these things quickly, cheaply, without sacrificing security, right? I mean, who's been on the receiving end of an audit where someone has ripped you to shreds, right? You get this report back, it's bad. And you'll basically get ripped on by the business side to get everything finished. And then you'll be ripped on by your dev team because they can't fix it either. And this is basically what we're doing. We're literally flying out of the pit, telling the devs to fix things, go on, right? Be brave little piglet and go into the woods, and yet they're not actually equipped to do any of these sorts of things. So we end up with these whack-a-mole types of security situations where we're focusing on bugs and problems, and we're focusing on bolting on security after the fact when we don't even have a design or an understanding of what we want to do or where we want to be at any given point. So it doesn't matter, right? We could build a house, and you'll just knock it down. We could do all sorts of things. Our tail will still float away. And in the end, we'll just basically be Eeyore sitting here because of the way that we've actually implemented these processes and the way that we've actually set up our departments. We'll end up with this sort of situation no matter what we actually try to do. So let's actually do something technical. I'm a technical person. I pretend to be friendly, but I'm not. So I thought we could actually talk about a history of keys and certs. So we know that we've needed keys. We need delegation. We need some way of understanding who is doing what and undertaking what action in some cryptographically secure way, right? So we've had this process for quite a bit of time. We've understood this from at least Kerberos times that you need some way of having a centralized system that can say who can do what at what given time, right? And we've had these for a while, but they actually haven't, they haven't necessarily been the greatest friends to us as well, right? So we had the NSP, right? That was part of Kerberos. There was a replay attack issue in that as well that Kerberos ended up fixing with timestamps. And then we have X509, right? So this is from 1988. It's 2016. We're still relying on this pretty much unchanged. It's hard to parse. It's hard to actually get right in any single way, and you can't technically control it, right? If you set up your own CA that's not an IA, that's not an intermediary, you'll actually be flagged in most browsers. And if you're doing certificate pinning, there's all sorts of fun that you can have there, or all sorts of problems that you can have, right? So we had this better system. It was SPKI, right? Came out almost 10 years later. It's super easy to parse. It's human readable. So you can look at a certificate yourself and understand if it's actually applied correctly. It's easy to control. You don't need to have a centralized system to actually implement any part of SPKI. And it actually includes a couple other interesting properties, which I'll get to in a second, right? So does anyone know what X400 mail directories are? Well, you're supporting them if you're using X509 certs, right? And this is what we're building our infrastructure off of. We're building it off of things that most of us, I was in short pants, let's say, when X400 came out, okay? Most of us have no awareness of these things. We don't understand where they come from. We don't know the historical facts of why we're supporting these things. We just have continued to build on top of them because we need to get stuff done, right? And it's extremely difficult to actually implement these sorts of things, right? Not even talking about things like Heartbleed and things like this. Parsing bugs, like ASN1 parsing bugs, it's actually surprisingly non-trivial to parse an X509 cert. If you want to have fun, and you're sort of into like a weird masochistic sort of like fun, try this. Actually go look up what the ASN1 parsing system is, and then try to implement it and see how far into it you get without actually having an edge case. And then another fun one too is to try to explain to someone quickly and correctly how to validate a certificate chain, especially if it includes IAs, right? And then you also have to think about the fact that you're trusting a large number of people here. You're no longer centralizing that control. You have all sorts of companies and government agencies that have root certificates that can issue things all the way down the train that you are now trusting, right? So this clearly has some problems, right? It's non-trivial. We can all think of SSL parsing bugs. We can all think of issues that we've seen with certificates, deploying them, maintaining them, etc. So we have this other system, right? This is great. This is 10 years later. Literally everyone in the room can look at this and figure out roughly how to parse this certificate, right? You may not have ever seen S expressions before, but you can pretty much figure out what each one of these areas is doing, right? I mean, it's pretty clear what an issuer, a subject, not before, not after is, right? And what's great about these is that you can actually encode access control lists, right? So you can have this very simple ACL. You can say this entry, it has a subject. That subject matches this hash. This hash should only be, or this subject should only be applied under these contextualized issues, under these situations. So clearly, we all should be using this, right? It's simple. You can encode a large amount of logic, right? But has anyone actually seen these deployed? There are two situations. One of them you probably have in your house right now, but you've never actually noticed that it's using this. So they're actually used in UPnP. So all of the like DLNA and everything actually ends up using these sorts of certificates. But they use an XML version of it. So they took out the simple part and then added all the other issues that you get with XML parsing. And a little bit of HP middleware. So if you actually have deployed HP's EasyTalk, you've actually seen these accidentally. And part of the issue is that because they're decentralized, because there's no role for certificate authority there, right? You can set up your own CA, you can set up the entire delegation chain, and it will work. There's not been as much excitement for these sorts of things, right? And beyond those two, there are no other mainstream applications of SPKI. So this is an easy to use, easy to apply, easy to understand system that no one is using, right? We're still going with the thing that encodes a bunch of stuff that none of us understand, none of us use, or probably some people do, or understand it at least. But, and we're ending up with this situation where we don't understand why we keep having these sorts of like parsing bugs and sorts of issues there. Now, Seth Law, he's our director of research at Invisium, and he told me my talk was too negative. So I thought I would take a short segue for a moment here to actually be positive here. Google is actually working on some interesting things here. They have macaroons and they have vanadium. So macaroons are basically chains of HMACs that are applied. They have some contextualization, and they're basically used in the same method as cookies. And then they also have vanadium, which is basically that plus some of the other ACL delegations that we saw in SPKI, right? So that's great, right? They're actually working on it. Has anyone actually seen or used or read the research on macaroons? Because I actually didn't know this until I accidentally ran into a friend who was working on this in Rust. So, and this is something that I've actually implemented SPKI before, and I hadn't heard of macaroons. I hadn't seen them before. So, we have these ways of building things and fixing things. We're just never going to do it. So, in continuing our train of a rainy day in the 100-acre woods, let's talk about operating systems, right? So when I think about operating systems, I usually divide things to like Multics, like before Multics, and then after Multics, right? And Multics, when it first came out, was actually a really interesting operating system. We'll talk about some of the security purposes, but it was a fairly modern operating system. It had two major drawbacks to it. It was extremely expensive to deploy, right? It came with specialized hardware. It needed to have, memory management units that would handle these sorts of things. It had all sorts of specialized hardware to help with the security controls that it implemented. And it was hard to develop for. And when I say hard to develop for, what I mean is that think about this, it's the 1960s, right? You're working on something that's usually just an assembly language that you just, you either do a punch card, you do something else, right? And all of a sudden someone is telling you, oh wait, hang on a second, you actually have to set the stack up, because the operating system does some stuff to the stack. And at the time, developers were not really interested in doing this sort of thing. But now, think about this, right? Where we are with modern operating systems, what do we want to have? We want to have access control lists. We want to have process separation, including at function level, right? We want to have like n-ary user space threads. We want to have stack separation, right? And we want to have high-level language support. Well, we actually had this in 1964. We've had this for, n number of years. And it's pretty good, right? Like, that's exactly what we want, right? We want all those things in a modern stack. That's exactly what we want to deploy, right? So, of course we don't, right? Because has anyone in the room used Multics before outside of an emulator? Because there are actually a few ways that you can use it. There are a couple clones out there that people use still. It's actually used in finance a little bit. So, how do we get Unix, right? And Unix was actually originally spelled with a CS because they were clones of Multics, right? They wanted to make something that was not a multi-processing system, or not a multiple computer, but instead it was just a unified one. So they removed all the hard stuff from it, right? Like, we don't need access control lists. We don't need a really fancy file system. We don't need a lot of that whole sorts of thing. We need something really simple that's really easy to deploy on the infrastructure that we have, right? We want something that we can take, we can port it all over the place, super simple for us to do, and we'll worry about the details later, right? So it was written in C. There was some bootstrap for assembly there, but C itself is pretty low level, especially if you look at K&R C, Kernighan and Ritchie C. It's very close to mapping directly to the assembly as well. So, we're just now in this day and age, we're just now getting back to where we were in 1964. We're just now starting to talk about operating systems that are written in higher level languages. I'll actually get into that a little bit later. And ACL is for everything, right? So think of SE Linux. Think of the various other control systems that we have there. You want to have these sorts of things. Well, we had them in 1964 and we gave them up because it didn't actually, it wasn't cost effective for us. We actually had a specification, so Multics was actually very heavily specified in the beginning. It was it had a very clear, defined, very close-cut actual way of working through the entire system. And it had true process separation at a time when most things were not really concerned about it, right? Think about how many years we went with 8086-based processors that didn't have actual process separation. And we tried to fix these things, right? So IX is actually a version of Sys9 Unix. It was tracking Sys10, System 10. And it was actually one of the first things infected with the Morris worm. So if you're familiar with the Morris worm, it was a buffer overflow across several different processes. And what was actually ironic about this was that IX was attempting to bootstrap itself so that it could boot into a secure Unix operating system. And one of the first things that happened was that it was actually infected with the Morris worm. And it delayed the release of IX for a decent amount of time. And then we also have Trusted Solaris, which I'm sure we've all at least seen. And there's Domain OS, which is actually a Pascal-based version of Unix that ran on some Apollo hardware. And it's funny, right? Because issues that we had originally in the original version of Unix, like PC losering, that's the PC register on a CPU, whenever you would switch back to a process, Unix didn't actually describe what the application was supposed to do at that point. So there's an entire syscall stack that we still do in order to work around PC losering because the operating system doesn't necessarily handle that for us. Now, we've gotten better over time, certainly, but we're still fighting with these same issues now that like ITS and Waits and other operating systems at the time had already fixed. And think about the Morris worm itself, right? This is a 1988 security vulnerability. Buffer overflow affected multiple processes, spread across the network, led to one of the first arrests for Computer Fraud and Abuse Act, and it's still something that we deal with basically today. So Windows is actually an interesting background, right? So Windows itself came from RSX11, from Dave Cutler. He brought a bunch of really interesting stuff over from OpenVMS. OpenVMS had things like asynchronous I/O. It had mailboxes, lots of interesting things, right? These are all things we wanted to have. But unlike OpenVMS and unlike like Multics, Windows was still implemented basically in C. You had all the exact same issues, and we also tried to bring over support for things like 9x and for DOS. And if anyone's ever done COM programming, handlers and like SC strings are basically your nightmare. Right? These are everything that's wrong with trying to do COM32 programming in a nutshell, very quickly. So, we've done all the really cool things that we wanted. We pulled all that really neat stuff from OpenVMS. We had this great infrastructure, and then we messed it up by including just a simple implementation detail of using a specific language. Now, in trying to be positive here, I do admit that we are getting here, right? We have OpenMirage, which is a hypervisor actually written in, or partially written in OCaml. So it's formally specified. It has proofs that it's actually doing what it says it's doing. We have SEL4, which is extremely interesting because they actually first went out, designed the model for how the operating system itself should actually switch. Like, so if it's doing inter-process communications, if it's doing anything there, they designed that in a environment called Isabelle, and then they extracted C code and Haskell code out of their model. So they started with the math, proved that they were doing everything correctly, and then they extracted it, right? And then there's also various efforts to have kernels written in Rust, in Haskell, in other languages such as this, right? But there's no point in caring about any of these sorts of things, right? Is anyone actually deploying on OpenMirage versus going to OpenStack or any of the various Linux, like Linux container systems that we have out there right now, right? No. There's a few of us, right? There's several people. Obviously, the people who are working on OpenMirage themselves are probably, are probably using it. They actually used it for ICFP, for all of their blogging platform. So any information that went out for ICFP actually went out over OpenMirage. But at the end of the day, very few of us are going to make that actual investment to switch over something that works in Java, in C, in something that we already know, to OCaml, right? It's different, very different language, very different edge cases, very different problems. So let's talk about network protocols. This is going to be one of those points where I actually get a little teary. I actually like the old days. I actually run a Gopher server. I have a framework. If you look on my GitHub, there's actually a framework for setting up and running Gopher instances out of Python in a way that's similar to Flask or Bottle, if you're familiar with Python web frameworks. But basically, we had these simple protocols way back when, right? A Gopher query is literally just a selector, some query, a bunch of tabs thrown together, a bunch of data comes back. HTTP was like, hey, that looks really cool, but maybe if we add a few things in there, we can get like a little better system, right? It's easier to describe what sort of data we're getting back. It's a little bit more flexible. And our login, whatnot. If you actually look at the protocol level, you can implement these sorts of things very quickly and very easily in the same area there. I'm sorry, I just love this. It has very little to do with protocols unless you consider the ringing as the protocol itself. I had to throw this in here. But we have all sorts of issues with these protocols, right? Notice not once in there did I mention anything about state, right? So if you issue a request to a web server, Gopher server, anything of that nature, it has no clue who you are. It has no clue who you are, has no clue where you were in the application flow. That's all implementation details, right? Which is great because it makes it really simple to get started, but it's painful because it's extremely difficult to program securely for it. That's why we have these entire bloated stacks that we end up using everywhere. The other thing is, too, think about how many different authentication systems are built into one web server, right? You at least have basic auth and digest auth, right? Digest auth itself has, 5 or 6 different ways of implementing it? You can have secure digest auth that actually sends a client and server nonce back and forth, right? Different hashing algorithms, etc., right? There's no presentation or discovery APIs, right? So we're still sending the equivalent of SGML back and forth, right? This is something from the 70s. We still send this back and forth, and we build applications on top of this, right? And then we wonder why there's actual issues there. And, we have data structuring issues that actually fly, right? So we have handling vulnerabilities that you'll see. This is like JavaScript, injection, HTML, whatever, like same-side server include. And I don't actually have anything to be positive about here. HTTP 2.0 will not actually fix any of these issues here. We can try to replace a core. We've tried to do this with DNSSEC, with Dane, with DKML, with lots of different ways. And we haven't come up with something that's actually stuck. So what we basically end up doing is we're taking all these other older protocols that may have fixed certain things, we just stuff them into HTTP, and then we wonder why we have vulnerabilities afterwards, right? So just be Eeyore. Just go back, do the simple HTTP 1.1, 2.0, however it comes out, and just run with it. It'll be easier, you'll drink less, and you'll just enjoy life a little more. So this is a little bit of an in-joke. At Invisium, I tend to ramble on more than I'm doing today. I ramble on about programming language theory quite a bit. It's something I've always been interested in. I implemented my first programming language, a compiler, in QBasic for Pascal when I was 13. But basically, we have these languages, right? If you're looking back through the mists of time into programming language theory, you can see these sorts of trends start out, right? So we have Algol 58 and MAD. We have Fortran, we have Lisp, we have COBOL, right? Basically the big 4 or 5 right there, right? Late 50s programming languages, and late 50s vulnerabilities, right? Like we never see these sorts of things anything more, right? We never see buffer overflows, right? Those are gone, right? We never see memory management issues. There's no heap spraying anymore. There's no computed logic errors anymore, right? We've eliminated all those things in the roughly 60 to 70 years since we've been doing this sort of thing. And even when you think about the first garbage collected language, right? You think about Lisp. One of the first things that they noticed about Lisp was that it was really easy to deny access to anyone else using the system, right? And it wasn't even like intentional. It was just like, oh, I loaded in too much data. I'm sorry, Bob. We've had these sorts of issues. We've never dealt with them. So in the beginning was the overflow, right? We had Fortran issues. We knew about this. We've actually studied buffer overflows as an area of study since 1972, right? And we're still dealing with them. Especially if you deal in the embedded space, you'll still see the same sorts of issues there. And the whole point is that when you have these programming language theoretic discussions, when you talk with someone who's super nerdy about it, you'll actually see that they do have implications or impact on your application security, right? One really super interesting one that came out recently was this Android compiler fingerprinting. And why it's interesting to me is the way that different compilers actually implement different semantics for C and Java allows you to figure out what the original developer was using to compile for that system. Super interesting. So we've gotten better, right? We're using more modern languages. We're using stuff from the 70s and 80s now instead of from the 50s and 60s. Even when you consider new things like Java, Java is, 25 years old? Heading towards 30 years old. We have Haskell, which is like at least from 1990. Standard ML, which just standardized a bunch of stuff from the 70s, is probably one of the newer languages on there. And it's still just making sure that everyone plays nicely as they're talking together. So we're not actually improving, right? We just keep writing these new languages and we're not necessarily looking at what the core of what we're doing here. We just keep writing and writing. So I thought it would be fun. I wanted to implement a program that I could understand. I think that this is about the level of program that I can understand and describe. So I want an array, right? I want to initialize that array with some, with some character value modularly, right? So, we go through A to Z and then loop back around, right? And I want to make sure that every axis of that vector is actually in there. Can anyone spot the bug? Right, exactly. So we actually overflow here by accident, right? Now, that's super simple. That's something really easy to do. How many times have you actually done this? The hardest things in computer science are like naming things, picking the correct algorithm, and off by 1 errors, right? Because there's only 2 hard things in computer science. So, that's why we come up with these fancy new languages, right? This is Rust here. If you haven't seen Rust, it's a new language from Mozilla. Graydon Hoare has been working on it. It's pretty interesting stuff. They have some interesting things going on here. So I implemented the same program here, right? And we come up with something really cool, right? I'm explicitly telling the compiler that not only is this safe to consume as an 8-bit integer, But afterwards, that entire calculation is safe to consume as a character, right? That's perfect, right? And this actually compiles and runs, or sort of. But it compiles, right? And we're hoping that a language that would require this level of like discipline and bondage would actually warn us when there's an off by one error in here. Unfortunately not, because although I have actually set up the array itself, I haven't actually initialized it to anything. And this is one of the first things that I actually ran into when I was trying Rust, was that I was looking at all these really cool new management techniques, and then I realized that I was not still handling the lower level issues that you would run into. Obviously, I saw something a little bit less trivial, but it was still in this similar vein. So even in safer languages, we can still hit these sorts of issues. We can't escape them, but we're hoping that the compiler will actually give us aid, or the language itself will actually help us to move beyond these sorts of things. And Rust itself does, right? I wanted to fix it because I didn't want to be one of those guys who comes up here and shits on something and then doesn't actually provide the way of fixing it. So there are ways of actually fixing the issue that I saw, and they're fairly trivial. But the language doesn't actually save you from doing it just yet. We want languages to save us from causing vulnerabilities. That's my aim, at least, right? So what I look for when I'm assessing some new programming language, when I see something has come out, I'm looking for the ways that we can formally verify this, what we can do modeling, the centralization of controls, and how I can actually understand those programs. And think about it. This isn't just like nerd stuff or like a bunch of quants. Like in finance, Haskell is very heavily used in finance. It's not that sort of thing. Imagine if you could model and do denotational semantics on your entire cloud. So you take all of the descriptors for all of your hosts, which is NICs, right? It's something like a dependency management system, but it's purely functional. You take some sort of descriptor for your software-defined networking, and then you could model across your entire infrastructure there. That would be pretty cool. No one's actually doing that. No one probably will do that because it gets really expensive. It's really hard, like we talked about earlier. But it is something that you could do. We're actually approaching that time when you could do those sorts of things. And it's actually something that you can get extremely wrong extremely easily. MITLS is actually a formally verified version of a TLS library. It's written by Inraya, which is the company, the organization that makes OCaml, and Microsoft. Believe it or not, Microsoft is actually a heavy user of OCaml, and they've actually come up with a formalized version of TLS, or an implementation thereof. And this page lists all the attacks that they've solved, right? And those include, when you actually look at it, those include things that are like logic state errors that are not encoded or not encodable in C. Those include all sorts of semantic issues that you could come up with. And those include just simple things like heartbleed, right? And all this they got out of just switching languages and formally verifying what implementation they're having here. So you can actually have better languages, right? You can have these sorts of better systems that fix the issue that you're having, that make sure that you're no longer entering into these systems or entering into these problems, right? You can have Rust, which, yes, I picked on here. You can have Wiley or ATS. ATS is an ML-based language that compiles directly into C. It's very low level. It's dependently typed. So you can do lots of proofs on your code, and then it will actually spit out relatively performant C code. In fact, for a while there, ATS was the fastest language on the Alioth language shootout, which was pretty interesting, right? Because you got this really ugly ML-looking code, and then it would suddenly spit out C, and it would be faster than the C implementation that was up there. We can actually even move on, right? We can move to Isabella and Coq. We can define I know everyone was waiting for me to actually pronounce that because they were wondering how I actually would pronounce that. But you can move on to these sorts of things, define your model, extract code, and then actually get reasonably performant, secure, semantically correct code. Use various new compilers, you can use better tooling, etc. And of course, none of us will do any of these sorts of things, right? We don't have the time, we don't fucking care. We don't have any of these sorts of, we don't want to do these sorts of things. That's really hard. I've actually gone through and verified some of the implementation stuff that I've done for my personal thing. And in the amount of time that I've spent, I could have actually gotten like Mike doing something useful like the entire time there. Yeah. I could have, in the amount of time that I've invested in proving that I did the right thing, I could have actually gone out and, implemented whole new features, right? I ended up with something that was extremely small and correct versus something that was broader and probably would have been better for what other people were looking for because I had to invest so much time in actually proving that I did the right thing. So I thought we'd actually do a thought experiment. This is one I've been running for like 10 years. I actually released code this time. This is a big complaint with me, is that I tend to sit on things academically. I know you're all surprised that I can be academic. But I thought I would do a thought experiment here. And I was thinking about, like, well, what would I actually do if I wanted to improve these things, right? So I've actually attempted this before. So I had a programming language called Digamma. Digamma was an extended version of Scheme, and it included some ways of actually modifying the execution environment such that if you were given an arbitrary piece of code, it could not, at a language level, could not escape the sandbox that you had defined for it. Now, obviously, you still have to define a properly secure sandbox, but you could prove that the sandbox that you had written was actually accurate and actually did what you were expecting it to do, right? So it had a security kernel that was small and formally verified. So I took all those ideas, I threw them away. I took 10 years worth of code and I just tossed them out. And I started working on another language, because this one will totally work out, called Caramel. And Caramel, I've actually added in Hoare logic, which is a way of doing the formal modeling that we had talked about there, with a little bit of a nicer, easier, more approachable syntax. And there's some ideas from memory management and Rust in there as well. And it's very similar to a programming language called Yeti. I know that I'm picking all the mainstream languages here for this talk, but Yeti is an ML dialect for Java, which has some interesting properties as well. So Caramel itself is actually basically, at this point, I know I said nicer syntax, I didn't say nice syntax, but basically we can define certain properties of a program, and not only can we pattern match on types and whatnot, but we can also use guards. We can use some extensions there to actually prove that our program is doing the correct thing. And it's been an interesting ride for me. I'm about 75% done with the parsing that I was interested in doing. So the language itself is roughly laid out. It has some rough semantics behind it, and we have some examples that I've already been working on. There is a prototypical compiler. It's not released. I didn't completely solve myself of that problem of not releasing code. But it's basically getting to the point where I was happy with Digamma and Typhon, which was the verified virtual machine that I had for Digamma, or the secure virtual machine that I had been working on. So basically, this is my attempt at solving the issues that I pointed out in the PLT section of this talk. It'll probably never get done. I'll find some other new shiny or something else to pay me that'll be better. But for now, this is my current experiment, and you can follow along on GitHub if you want. The other thing that I've been playing with is a protocol called WhistlePig. WhistlePig is so named because my girlfriend hates this word whenever I say it. But basically, it's a combination of Gopher and 9P. 9P is the file system protocol that backs Plan 9. So Plan 9 had this file system protocol that you could use, and it was basically used for everything. So once the kernel had started, everything, including networking, was based off of this file system protocol. So WhistlePig has some ideas from there. I've started working on how keys and certificates are implemented. I am using SPKI for this from the start, and the basic specification for WhistlePig itself is actually up on GitHub as well. So I'm trying to be better and actually release things and see Mike is laughing at me. But basically, this time around, I thought I would try and experiment differently and actually release things and see what else people can actually come up with based off of what I've been doing. So I'm actually done. I'm getting close to the end there. And I thought I would just surmise what you should be getting out of this. So nothing that I've talked about will save you. we're basically all left to our own devices to actually get out there. There's no meaning to security. You're all probably going to get hacked at some point, even if it just means that you're hacked by some guy walking out with an entire stack of papers there. We all die. There's no way of getting around that, sadly. And also, work is not going to be great either. So even if you do all these sorts of things, even if you go out and implement an entire formally verified process, you'd still have all the same sorts of problems that you had here. They would just be different ones and more painful ones, because you'd also be fighting with the compiler to prove that you actually know what you're talking about. But at the end of the day, at least you would have a really nice, pretty graph that would show that you had actually done all this work there. So that's all I have. Does anyone have questions for? Yes, okay. Well, so my problem with academia is twofold, right? Because I actually used to work in, I know surprisingly, I used to work in academic settings. The thing that I noticed about academia is that, A, if you're not chasing the hot thing that your advisor is chasing, you may as well not exist, right? You're not we have some heads shaking. You're not going to get money, lab time. You're not going to get support. They won't read your papers. You'll have hard times getting peer review. The other thing is actually peer review. So because of the nature of academia, right, if I want to send a paper to Mike, but Mike is working in the same realm, I basically have to trust that Mike is not going to see something, make some connection to something that he's working on, and then run off and actually fix a problem I've been having. So Mike may have fixed something, I'm having a different problem, and when I exchange papers for him to review, there's that. The other thing is, too, academia, believe it or not, tends to have a very short shelf life. So you work in academia, you do something interesting, and then the rest of your career, you're chasing that publishing high. So you're trying to make sure that your paper mill is coming out, that you're getting cited, you're being cited by, you're collaborating, you're chasing grants. So it can be very painful to actually try to keep up with it. Have there been fixes to these sorts of things? Yes. The other problem with academia is often that it's academic. So they don't necessarily have to be focused on being performant, on being something that you could release or use. So it's like, I have this one box, I've designed an operating system for it. It literally can only run on this box. I have no idea how to port this off of this box. One of my grad students actually wrote the bootloader, and I forgot. So yeah, I mean, we totally can do these sorts of things. We just won't. Yeah. So does that answer your question on how I'm nihilistic about that as well? Does anyone else have any other questions? Sure. And by the way, just one, I'm sorry. I'm actually extremely hard of hearing, so if I mishear what you say, it's not because I don't care, it's because I can't hear and I don't care. But no, please, what were you going to say? I'm sorry? So, I presume you've actually programmed in Ada, right? Okay, so we have two people in the room, because I'll include myself. Has anyone else actually programmed in Ada before? Okay, we have 3 people in the room. Has anyone programmed, was it large or was it in college? Yeah, okay. And was yours was like an actual product, or, yeah, so I did one stint on an Ada program, okay? It was miserable. It was extremely difficult to get the compiler to do half the things that I wanted to do, right? I was actually tasked with making sure that the RC4 algorithm was implemented correctly in some subsystem that we were working on. I just remember wanting to cry, mostly crying. Yeah, it was pretty bad. I mean, Ada's great. Ada has a lot of the stuff that we would be solved. Things like Spark and Ravenscar, those are really great subsets of Ada itself. So Ada can define smaller portions of Ada itself, smaller portions of the language. And Ada has that ability, and there's some great areas that you can do. every time I've worked with it, it's been more painful than anything else. It's also probably the language I would look to compare anything else to. So if you can't solve what Ada has solved for us since 1983, at least Ada 83, Ada 85, if you can't solve those sorts of things in your language, I would kind of question being formally verified or having that sort of level of support there. So, yes, I have programmed in Ada, but it was existentially draining. Anyone else have any other questions? Well, perfect. I'll give you back sometime, but thank you very much, everyone. I'll be milling about, and you can always find me on Twitter spouting my security nihilism as well.